Hi everyone, I'm trying a new microphone. Let's see if the quality of the audio improves. In this video lecture, we'll start to fulfill some of the promises we made last week about the properties of the Lebesgue integral. And today we'll see the main theorems about convergence, which allow essentially commuting limits with integrals. And the two main cases are the monotone convergence theorem and the dominated convergence theorem, which, as we mentioned in the first week of this module, the monotone convergence theorem appears in the world where we consider non-negative functions. This is the main convergence theorem for non-negative functions. And the dominated convergence theorem, it belongs to the integrable world. And as we'll see, one thing that can happen in measure theory is that we can lose mass, and theorems of convergence, they deal essentially with that situation. So here is a function f. This function f, if we draw the axis like this, and we draw this curve, any point we pick on this curve, we look at the rectangle that determined by that point, the area of that rectangle equals 1. So area equals 1. Well, for the only curve that has this property, you can guess it already, is the curve y equal 1 over x, of course. That's when it will have area equal 1. And as we move this point here along the line, each time we find a rectangle whose area equal 1. The problem is this is not preserved in the limit. As we make this point go higher and higher and higher, eventually we'll get a point which is at infinity, and with zero, we get a rectangle which with infinite height and 0 width. So the width is 0, the height is infinite, and we can't assign any area to this rectangle besides area 0. It has area 0. So this is what this sequence of functions here represent. We are taking 1 over n, and then we take height n. The area is always equal to 1, which means that the integral of this function with respect to Lebesgue measure on the real line is always equal to 1. But now, as we let n tend to infinity, this function approaches a function age, which is 0 if x is not 0, and plus infinity when x equals 0. And the integral of this function h with respect to the Lebesgue measure is 0. So you see here the integral of this function is always equal to 1. And then we take a limit, and we see that the limit of this integral is different from the integral of the limit in n. This limit here is exactly the function h. So the limit of the integral was not equal to the integral of the limit. It was larger. And here it is always equal to 1, and suddenly when we pass to the limit, this integral becomes 0, so we can lose mass. Now here is another way we can lose mass, is the following. Consider now this function. I'm adding an index n here to make it easier to talk about it. So this function gn, it takes values 1 on this interval between n and n plus 1. And then it takes value 0 before and after this interval. Of course, if we compute the integral of this function gn with respect to the Lebesgue measure, what we get when we get this area here this is also equal to 1 for every n. And however, we can now think, what is the limit as n tends to infinity of this function gn? So for each x fixed, so we fixed x, we can take the limit when n tends to infinity of this function gn of x. And what will be that limit? Well, we fix x here. Let's fix x. What is the value of gn of x? Well, it is 0 when n equal 1, then it's 0 again, then it's 0 again, then it's 0 again, then it's 0 again. Well, at some point it will be 1 when we take this function gn here. It will be 1, but then after that it will be 0 again, 0 again, 0 again. It will be 0 forever, which means this is 0 for every x. For every x, this limit is 0. So this is the same as saying gn converges to g, where g is just the 0 function. So, and that's quite strange, right? The integral of g is 0. So we see the integral of the limit was different from the limit of the integrals. And we had functions that always had area 1. We had these curves, they always had area 1. And in the limit, they converge to a curve that has below them an area which equals to 0. So we can lose mass. Measures can lose mass. And we want to understand in which situation it can happen and in which situation it cannot happen, which is the most interesting. Here's the monotone convergence theorem. What it says is we cannot gain mass in the limit. We have just seen two examples where we would lose mass. In the first example, we would lose mass, let's say, vertically, because we're considering these regions like this, and this mass, it disappeared, it went to infinity. It went to infinity vertically, and that's how we lost it. In the second example, we lost mass horizontally. It went to infinity, but it went this way. And what the monotone convergence theorem says is, yes, it's possible to lose mass, but it's not possible to get mass. And in which context? Well, first of all, in a context where it makes sense to talk about mass and mass. So we're talking about non-negative things and increasing. So we have a function, fn, and then we have a slightly larger function, fn plus 1. Then we have maybe some slightly larger function, fn plus 2. And then perhaps some even larger function, fn plus 3, and so on. And so these are increasing. And well, increasing sequences of numbers, they always have a limit. Likewise, increasing sequences of functions, they always have a limit. So if fn is an increasing sequence, we can always write this arrow up here, and it always converges to something. That thing can be infinite at some points, but that's why one of the reasons why we incorporate infinite in our space. That's why we like so much to work with this space, is that infinite is a point there, so we can make bold claims such as every non-decreasing sequence converges, because it converges on this space where infinite is allowed. Okay, let's continue. Fn is an increasing sequence of functions, so it has a limit. Let's call f that limit. Of course, for each fixed n, the function fn is bounded from above by f, because this f is what you get only in the limit when you keep increasing after n. And because of that, the integral is also bounded by the integral of f, and we can take the limit here in this equation. So just from these simple observations that fn is bounded by f, taking the integral, then taking the limit, we see that the limit of the integrals of fn cannot be larger than the integral of f, which means we can never gain mass in the limit. What we could do possibly would be to lose mass in the limit, but here we cannot lose mass either, because the limit of these integrals is smaller. So the integral of f will be at least the integral of f. So what is missing here is to prove is that what happened in the other previous example of losing mass cannot happen when we have a monotone sequence of functions. So when the functions are increasing, that thing cannot happen. And by this elementary principle here, you cannot get mass either. Okay, so this was interpretation and discussion. Let's really discuss just what the theorem is saying. So if we have a non-decreasing sequence of functions, we can talk about the limit of those functions because they're non-decreasing. We can integrate that limit because the limit of extended Borel functions is an extended Borel function. We can integrate it, and what the monotone convergence theorem says is, well, we could integrate each of these functions alone, compute the integral, and then take the limit of those numbers. So here we have a limit of numbers, whereas here we have a limit of functions. And how can we prove the monotone convergence theorem? Well, one inequality we did already when we discussed the motivation. That was a rather simple. Fn is less than f, always. And because Fn is always less than f, we can integrate, and it will still be less than f. Now I'm talking about any measure. Let's write mu, because it can be any measure. So because the integral is monotone, we have, this is an axiom of the integral of non-negative functions. So we have this inequality for each number n. Since this inequality holds for each number n, and inequalities are preserved by the limit, or non-strict inequalities are preserved by limits, so we can take the limit here on both sides of this inequality. I'm not going to write the limit on the other side because it doesn't depend on n. So this direction, we have it already. Okay. So now what we need to show is the other direction, is that this integral, this limit is at least equal, this limit will be at least equal to the integral of f. And now let's hold this proof for a later video lecture and give a dirty proof of it, which is based on the axiom. We assumed that the Lebesgue integral of non-negative functions is sigma additive. And well, in order to prove that axiom, we'll see later, we actually need to use the monotone convergence theorem, but let's hold that proof for now, and for now just prove it using the axiom, which is kind of cheating. So let's do the following. Let's define a function, let's call that function g1 to be f1, then g2 to be f2 minus f1, g3 to be f3 minus f2, and so on. Why am I doing this? Because then we have fn equals g1 plus g2. We know, you see, when we add g1 and g2, these cancel. Then we can add g3, and these will cancel, and we can keep adding until gn. When we do this, then it becomes very convenient, because now when we integrate fn, we get this, and if we let n tend to infinity, this will tend to the integral of g1 plus to this series. Here, if we let n tend to infinity, then this is a partial sum of a series, and it will converge then to the sum of the entire series. This on the one hand, but on the other hand, because we assumed that the integral is sigma additive, we have that this infinite sum here equals also the integral of this function, and this function is exactly f. And this will conclude the proof, because now what we showed is that we started with the integral of fn. We express it as a finite sum where we're only adding more and more terms in the end. We take the limit of this expression for the integral of fn. We get this infinite sum of integrals. Now we use the property again of the integral being sigma additive, and we see that this function that we're integrating here is f, which means this integral here equals the integral of f. So what we have proved through this path is that the integral of fn converges to the integral of f, which is the content of this theorem. I remember when I was a student and I had to know all these theorems and have them ready to use at any point. Then there were all these theorems, and I wanted a very short way to remember them. And a short way to write all this blah, 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 blah is non-negative, fn, non-increasing, non-decreasing, so it increased to something, increased to, well, call it f. This implies the integral of fn converges to the integral of f. That's a short way to write what is the statement of this theorem. You may prefer to have both options to work with.